Good afternoon, this is Mr. Schweitzer, and this is just a general overview of our latest chapter on equilibrium. First of all, just again review what is equilibrium. It is a competition between usually for us, two processes, to keep it simple. And we only have a certain few types of equilibrium that we would really even consider looking at. One is the first one we just did is solubility. And we have a solid on the bottom, stuff dissolving, stuff returning in here. Two competing processes usually only works for things that are slightly soluble. This is called KSP, and we would measure the concentration of these guys, so that's something we just got done looking at. Another type of equilibrium might be of something evaporating. If we have a liquid here, it's a closed container, and we have gases exiting, gases returning. The pressure in here equals, we call this the vapor pressure, all right? And at this point, we're dealing with gases. So we'll possibly see some examples of this as we go along, although the idea is more what we might think about, that as we establish this, we get a number of gas particles building up inside here. Maybe nothing or next to nothing is exiting, returning to the solution. Then as it builds, occasionally they start to return. And eventually they start to return at a rate that is equal to the rate which they are exiting, and we form a static pressure. If you were to chart the pressure, it would be increasing also would level out. And this leveling pressure is the vapor pressure. This chapter is going to be looking more at just a general type of equilibrium where we have a typical item converting to another item and they're both in solution potentially, where we have squares and triangles representing a conversion back and forth between two items. These things could be typically dissolved, but could be gases as well. So we call this typical type of equilibrium KC. C stands for concentrations. All concentrations will be in moles per liter. Again, you might also see it as KEQ, just your standard equilibrium. Very typical type of reactions. We have another version that we'll use to monitor, an equilibrium, which would be involving gases. Gases can be measured in Kc as well, but they can also be measured in pressure. For example, if you were monitoring the pressure of this thing, you'd see the pressures were changing. All of a sudden, right here, equilibrium was established, and there's no more changes in pressure. So in this case, for this chapter, we want to be able to write K expressions for both pressures and for concentrations. So I could have, for example, A gas plus B liquid yields C aqueous plus D 2D gas. So I have a solution here. If I were to write the Kc expression for this, I would include anything that has a concentration in moles per liter. D is a gas, so bracket D squared. C, aqueous, definitely has a concentration, bracket to the first. Liquid, liquids don't have a concentration, it's out. Gases, A, bracket to the first. If I were to do a Kp for this thing, this means that all my units are in pressures. I can only include things that have pressures, which is just gases. It's going to be equal to the concentration of D squared cannot include C. Okay, on the bottom side, liquids cannot include liquid, and A has a pressure. Now, because we're dealing, I'm going to erase this, because we're dealing with pressures, I cannot use the brackets. That's something I got to catch myself on too. We would use partial pressures, so as the individual pressure contributed to or because of D, and it would be squared. And then it's the partial pressure of, or the pressure contributed by A, and it would be to the first. This is how we do it, and it's the partial pressure. So inside of a container, all right, we're going to have some both. They're going to have some A's in here. Okay, and I would even say that this particular item's got a liquid in it, and therefore would be referring to in this enclosed container. Oh man, lost my whole container there. Okay, it's enclosed. Some A's are up here, and we'd have some D's, which are products, up here. And what's the ratio of D's to A's? Of course, we're squaring here as well. So I wouldn't be able to put my total pressure, because the total pressure would be the same for D in the container. It's one container. So I want to know what of the total pressure, what portion of that pressure is due to D, what portion of that pressure is due to A, and that's called your partial pressure. Keep in mind, PV equals nRT. If we put just the moles in of D, we get the partial pressure of just D. All right, and then finally our last main topic would be a quiz topic, would be on what happens if you disturb equilibrium. Well, if you disturb equilibrium, meaning that, let's say, for example, you have a teeter-totter and we're in balance. Now I draw it straight here, it's in balance, okay? And all of a sudden you throw, and this is where the teeter-totter wants to be, or in nature it wants to go flat. Well then, if you throw some extra bricks on one side and it ends up falling down, nature is going to work to go back to its original location. So it might work to push some bricks to the other side, at least one of them, so that we are back to being like this. Again, I can have some bricks on one side, but keep in mind, the original, this is still the same as this. We are balanced. Okay? So I could have a balancing act of a whole bunch on one side as long as I have the whole bunch on the other. And I'm still balanced. My K, if this represents my K, then this also represents the same K. And so does this represent the same K. So it's a ratio. So whenever you disturb, this is very important, whenever you disturb equilibrium, what you're basically saying is you are taking it out of equilibrium. You're doing something to make it no longer in its balance, which is what we measure as in K. So what this thing wants to do is it wants to return to equilibrium, as all nature does. So whatever you did to this thing, it will try to undo. If you add something, it will try to remove it or balance it. If I add bricks to one side, it will attempt to remove bricks from that side, put them on the other side, in order to, again, retain balance. So common examples of this would be if you add concentration, then it will attempt to remove concentration. If you add pressure, it will remove pressure. So if we look at a reaction, K, let's go with this example we have up here, with A plus B plus C plus D, that guy. If we do anything to disturb these concentrations, then this process will work to regain the concentrations. Now, if I were to add C, well, then I have too much product. So it's going to try and shuffle C and D together, shuffle those back over to reactants. So we're looking at things that if we add they call it a stress. And if we add a stress, that will undo the stress. This whole thing is called Le Chatelier's principle. This whole idea of undoing is called Le Chatelier's principle. It is, to me, one of the easier topics that we could possibly deal with. So if you find yourself struggling with it, make sure you get some help on it, because it's an easy fix, and you should be an expert at Le Chatelier's principle. And that's just a general overview of, we're just taking and adding in a couple more little processes. This idea of gases, and maybe some little bit more involved types of equilibrium, and then the Chatelier's principle. So a smaller yet important chapter.